everyone. My name is David Lieberman.
And I'm Mark Remmelman.
I am the owner of Computer Methods and one of the software developers for PhoenixKonnect.
And I'm an industry application specialist. I've got over 30 years of high-speed data acquisition experience. I'm working with Computer Methods and PhoenixKonnect Technologies. And today we'll be demonstrating the PhoenixKonnect application running on multiple hardware platforms.
So we have here our test fixtures, and Mark is going to explain the hardware configuration.
So over here we have the PhoenixKonnect system. It's the ALI 25. It is a 5 megasample per second, 24-bit, with the WSB card next to it. That is a high-speed streaming device, 200 kilosamples per second, 24 bits, handles both bridge condition and ICP. Here we have the Spectral Dynamics high-speed VXI system. It's been the gold standard in the industry for over 20 years. Both systems are run by the PhoenixKonnect application. And for size comparison, the VXI, this is 8 channels, and this is 8 channels of high speed and streaming card in a much smaller form factor.
So Mark, I see a row of caps here. You want to explain what's going on with these?
Certainly. Glad you asked. So these caps are used for generating a miniature explosion. We have a low-tech detonator, a little fixture to put the caps into to make the explosion. That all resides in this little hole here. It's sitting on an aluminum plate, which has strain gauges mounted in it. From that aluminum plate, there's 2 shock accels. They're co-located so that one will be going in the positive direction, one will be going in the negative direction. With this application, we can overlay, reverse the polarity. They'll line up on top of each other. At the top of this tube, we have a high-speed pressure transducer manufactured by PCB. And what happens is when we set off the explosion here, the shock wave will move up the tube, and because it's going through a tube, it becomes a laminar flow shock wave. So we have one common shock front across the top of the tube. We'll measure the overpressure from that.
And I also see another fixture here with a red bell. You can explain what's going on over here.
So here we have another high-speed shock accel manufactured by Endevco. And inside are a microphone, and when you set it off, we'll actually be able to see the shock wave of the bell ringing. Okay. So we're loaded, caps are in here, locked and loaded, ready to go. 3, 2, 1.
Three, two, one. Okay, so we captured data on the 4 channels we're worried about. Starting at the bottom of our screen right here, we see the blue trace. That's the microphone / pressure transducer at the top of the shock tube. We got a nice response out of that, the cap going off. The next trace up is the green strain gauge response, and it is exactly what one would expect when a bolt is hitting and pushing down. It's in the negative direction. The top 2 traces, the red one is the gas damped accelerometer, so it has a limited bandwidth response. And the top trace is a broadband accel, which is not damped, so it is prone to resonance. And we will get into looking at the resonance here in just a moment. So now we will remove the 2 graphs we're not going to worry about at the moment. And if we zoom in on this, you can see the very dense black areas on the top trace. That is indeed resonance. We'll zoom in a little more. We have this nice little sine wave riding on what is essentially this waveform. The key reason for having a broadband data system is to know if you indeed rang your transducer, because this sine wave will cause a lesser capable system to have what's called slew rate limiting. And it will indeed distort the waveform you're interested in. So moving along now. I'm going to just concentrate on the broadband Excel. First thing I'm going to show you is the resonance. And we can see our peak. And there we go. So with this resonance in the image, in the data, it's hard to compare the two transducers. So what we're going to do is remove the broadband response of this transducer, the resonance, by doing a filter. But we're going to bring up the second trace also, the other transducer of interest. We'll set them up so that they're stacked so it's easy to see. And now we're going to go ahead and filter. We're going to filter them to 30 kilohertz, which is the usable bandwidth of the gas damped transducer. So we've now filtered the broadband Excel. And now we have filtered the gas damped Excel. We'll remove the broadband raw and the gas damped raw. If we go ahead and now overlay the two transducers, you can see they lay right on top of each other. This verifies that indeed they're truly co-located, and it is possible to get exactly what you need using either a broadband transducer or gas damped, so long as your frequency of interest is within the usable bandwidth of the transducer. Okay, so I brought up the graph of the pressure transducer because there is some interesting features in the data and the capability of the data system. As you can see, we have a very fast rise time here. If I had better caps like I used to back in the day, we would have a much higher pressure waveform, but this works. Let's zoom in on it a little bit. And we'll just bring it in a little bit more. So we've got a fairly fast rise time. And if we go ahead and go to dot mode here, we can see that each of these is a sample. We're sampling at 5 megasamples per second. So that's basically 200 nanoseconds per sample. if we actually measure the time between beginning of the rise and the peak, you can see that we are at 2 microseconds. That's the equivalent of 500 kilohertz. That's a very fast response. And when one's looking at pressure data, it's key to know the capability of the transducer you're using. So this transducer I've tested, it'll actually do a megahertz.
Mark, thank you for demonstrating these systems today.
Well, Dave, I hope you got a real bang out of it.
Yeah, I did. I enjoyed it. And for more information, please refer to the links below on your screen.